You walk past it, like, literally all the time without even noticing.
Oh, absolute.
You drive past these towering petrochemical plants glowing in the night, or you see heavy military hardware on the highway.
Right, or even just looking at the complex industrial plumbing in the basement of, like, any high-rise building.
Exactly. And you rarely stop to think about the sheer terrifying physics at play there. I mean, you have these massive high-pressure metal structures enduring intense heat, crushing loads, corrosive weather, all of it.
Yeah, and under those extreme industrial conditions, metal naturally wants to bind.
Right, because at the microscopic level, if you have two steel flanges under thousands of pounds of pressure and hundreds of degrees of heat, they will literally attempt to share electrons. They want to fuse together.
Which is a nightmare. Preventing that kind of catastrophic cold welding isn't just about structural design. It really comes down to this highly engineered, black, petroleum-based paste.
And that brings us to today's deep dive. We are pulling our insights directly from a dense engineering document, specifically the technical datasheet for JetLube 550 Extreme Anti-Seize Compound.
It's quite the document.
It really is. Our mission today is to decode the high-stakes science of extreme lubrication hidden in these specs and, explore how predictable friction is kind of the unsung hero of modern infrastructure.
Yeah, the datasheet introduces this product as a low-E enhanced formulation. So it's designed to conquer environments that would just completely destroy ordinary grease.
Right, to save countless man-hours in assembly and dismantling. But before we get into what this compound can survive, we have to understand how it's actually built.
It's all about the recipe.
It is. I like to think of it, and this is my own analogy, but it's kind of like baking a cake that has to survive a trip into a volcano.
That's actually a pretty good way to put it.
Right. Okay, so let's unpack this. What exactly is a calcium sulfonate complex base doing for us in this recipe, and why does it need synthetic graphite?
Well, looking at the composition, what stands out immediately is how it completely deviates from standard lubricant construction.
How so?
In a typical grease, the base is really just a dumb carrier. Usually a cheap mineral oil whose only job is to suspend the active friction-reducing solids.
Okay.
But the 550 Extreme relies on a calcium sulfonate complex base. This base is an active structural participant. It's not just sitting there.
The text mentions it provides inherent anti-wear properties and acts as a fortress against rust and oxidation. But mechanically, how is a base fluid acting as a rust fortress before we even get to the solid additives?
It comes down to molecular geometry. Calcium sulfonate molecules are shaped somewhat like microscopic tadpoles.
Wait, tadpoles?
Yeah, tadpoles. They have a highly polar head that regressively, physically binds to the metal surface, while the long, non-polar hydrocarbon tails point outward.
Oh, wow. So they form a layer.
Exactly. When you apply this compound to a bolt, millions of these molecules align to create this bristly, microscopic barrier. Because those outward-facing tails are hydrophobic, water and oxygen molecules literally cannot penetrate down to the metal surface.
They just can't start the oxidation process?
Right, it stops rust before it even begins.
So the base itself is doing some heavy lifting by sealing the metal pores, but the datasheet also lists surface-modified synthetic graphite and molybdenum disulfide as the primary solids in this volcano cake.
Right, the solid additives.
Yeah, so if the calcium sulfonate base is already protecting the metal, what's the specific mechanical function of adding those two solids into the mix?
Well, while the base prevents corrosion, the synthetic graphite and the molybdenum disulfide, which is commonly just called moly, they manage the physical friction.
Okay, so they handle the sliding.
Exactly. Moly disulfide has this lamellar structure. If you look at it under an electron microscope, it basically looks like tiny stacks of playing cards.
Okay, I can picture that.
So when two metal parts try to scrape against each other under immense pressure, those microscopic cards shear off and slide past one another. They allow the metal to glide smoothly, even when the clamping force is actively trying to crush the joint together.
That structural architecture explains another key spec listed here, which is NLGI Grade 1. And the manufacturer notes that because of this highly specific chemical makeup, the compound won't harden, evaporate, or settle out over time.
Right, it's incredibly stable.
Yeah, it requires absolutely no thinning. You pop the lid, and it's ready. And that consistency is largely due to its NOVOC formulation, meaning it contains zero volatile organic compounds.
Which is a huge deal. Eliminating VOCs fundamentally changes the life cycle of the paste.
Because the VOCs are the solvents.
Exactly. They're the solvents that evaporate into the air over time. In older anti-seize formulations, as those solvents flashed off, the paste left behind in the bucket, or worse, left behind on the machinery, would dry out.
It would just turn into a solid brick.
Yes. Removing them ensures the rheology, the flow and thickness of the paste remains permanently stable. And as a bonus, it meets modern environmental compliance standards.
Now that I know the ingredients, I want to look at how tweaking just one of them changes everything. I actually want to push back on the molybdenum disulfide ratio for a second.
The moly paradox.
Yeah, because the datasheet explicitly warns about the danger of high molybdenum products. My instinct is, more of a good thing should be better, right?
You really think so?
If moly acts like sliding decks of cards to reduce friction, why wouldn't JetLube just pack this stuff full of it, like well past 40% moly, to get friction as close to zero as possible?
What's fascinating here is that this is a brilliant example of counterintuitive engineering. The goal of an anti-seize compound used on structural fasteners isn't to eliminate friction entirely.
It's not.
No, the goal is predictable friction. The source material outlines that if an anti-seize compound has greater than 40% moly, it experiences these substantial friction function drops during hot torquing.
Hot torquing meaning the process of tightening bolts while the machinery is actively running at high temperatures.
Precisely. The datasheet highlights a very specific danger zone between 250 and 400 degrees Fahrenheit.
Okay.
When a high moly compound hits that thermal window, the heat fundamentally alters the way those microscopic lamellar layers interact. The friction resistance just drops off a cliff.
Oh, so the compound becomes unpredictably slippery?
Exactly.
So let me picture this. An engineer applies a specific amount of turning force with their wrench, expecting a specific amount of tension in the bolt.
Right.
But because the machinery just heated up to 300 degrees, the grease suddenly loses its resistance. The wrench turns way further than calculated.
And the engineer inadvertently stretches the bolt right past its yield point.
Wow. Which could snap a primary fastener on a high-pressure line.
Exactly. And that's catastrophic.
Excellent.
550 Extreme is engineered to solve this precise issue. By keeping the molybdenum levels strictly balanced with the synthetic graphite, it's less sensitive to temperature.
So the compound's coefficient of friction remains virtually flat across these massive temperature spikes.
Right. The math works the exact same way at ambient temperatures as it does at 400 degrees.
Since temperature causes that unpredictable behavior, I really want to transition into exactly how much extreme physical punishment this specific formula is proven to withstand.
The testing metrics are wild.
They really are. Here's where it gets really interesting. We see a 4-ball weld point of 800 kilogram force with a load wear index of 100.
Which is massive.
To a layperson, an index of 100 might just sound like an arbitrary perfect score. How does that actually translate to real-world mechanical pressure? It sounds like a medieval torture chamber for grease.
It kind of is. The 4-ball weld test is the standardized method where 3 steel balls are clamped together in a triangle and a 4th ball is pressed down into the center of them and spun at high speeds.
Oh, block sounds intense.
The machine continuously increases the crushing load until the lubricant film between the balls completely fails. When it fails, the metal cold welds and seizes the machine.
And where do standard greases usually fail?
Standard industrial greases might hit a load wear index of maybe 30 or 40.
Oh, wow.
Yeah, so hitting an index of 100 means the chemical barrier, those calcium sulfonate tadpoles and moly playing cards, remains intact, even when the machine is applying point loading that should, by all laws of physics, completely fuse the steel.
That is incredible. And it also survived the sulfide resistance test. It endured 500 hours in a 20% sodium chloride solution at 100 degrees Fahrenheit without a single trace of corrosion.
That's like leaving your car parked in corrosive sea spray for weeks.
Exactly. And alongside that, it scored a 1A on the copper strip corrosion test, proving the chemistry doesn't cannibalize the softer metals it's actually designed to protect.
Which is a delicate balance to strike.
But looking at the thermal operational window in the specs, I'm seeing numbers that seem almost contradictory. Like, it's brushable down to negative 10 degrees Fahrenheit, but in static applications, it functions down to negative 265 degrees Fahrenheit.
Yeah, the cryogenic capabilities are fascinating, especially when you consider petroleum fluid dynamics. At negative 265 degrees, almost all hydrocarbon carrier fluids will hit their glass transition phase.
Meaning they solidify and essentially shatter under pressure.
Exactly.
But I would assume if a compound is engineered to survive cryogenic freezing, its high-end thermal tolerance has to be severely compromised. I mean, materials rarely excel at both extremes of the spectrum.
Normally, that assumption absolutely holds true. But the datasheet indicates 550 Extreme can survive up to a blistering 2,400 degrees Fahrenheit in select applications.
Wait, 2,400 degrees?
Yes. It also lists a specific gravity of 1.22, a density of 10.2 pounds per gallon, and a dropping point of 450 degrees Fahrenheit.
The dropping point is the temperature where the thickener releases the oil.
Right, versus a flash point of greater than 430 degrees.
Okay, so what happens between that 450-degree dropping point and the 2,400-degree maximum survival rating? The base fluid has to be long gone by that point.
Oh, the carrier fluid absolutely burns off or volatilizes away at those extremes.
So how is it still working?
Remember the solid additives, the synthetic graphite and molybdenum disulfide. Even after the petroleum carrier is completely gone, those solid, microscopic lubricating plates remain embedded within the pores of the metal flanges.
Oh, I see.
They continue to provide a dry film physical barrier that prevents the steel from fusing, even as the environmental temperature literally approaches the melting point of the metal itself.
Having established just the immense durability of this compound, let's bring all this laboratory data down to the actual wrench turning on the job site.
Yeah.
How engineers apply this.
Right, the practical application.
So what does this all mean for the engineer with the wrench? The text includes this mathematical formula. T equals K times D times F, where T is the torque, D is the bolt diameter, and F is the bolt tension you want to achieve.
The standard torque equation.
Right, but the entire equation hinges on the K factor, and the source explicitly makes a fascinating correction here. It clarifies that K is the nut factor and notes it is often incorrectly called the friction factor.
This raises an important question about safety and efficiency. The distinction between friction factor and nut factor is really the difference between academic theory and field reality.
How so?
Well, the friction factor only describes how slippery two surfaces are against each other. But the nut factor, K, is a dynamic, holistic variable.
Okay, so it includes more than just friction.
Exactly. It accounts for thread pitch geometry, the metallurgical properties of the fastener, and how the anti-seize compound's rheology fundamentally changes under immense compressive loads. Torque repeatability is critical here.
I'm looking at the data table provided for 1-inch uncoated B7 studs. The varying K factors actually change dynamically based on the tension being generated, which is measured in kc, or kilopounds per square inch.
Right, look at this spread.
At 80 ksi's of stress, the nut factor is 0.15. But if you're generating less tension, say 50 ksi, the nut factor rises to 0.18. And down at 30 ksi, it's 0.19. The harder the engineer squeezes the joint together, the lower the K factor drops.
Because as the compressive force increases, those molybdenum and graphite plates are forced into tighter, more uniform alignment that continuously alters the rotational resistance.
So an engineer has to map their calculations against that specific dynamic curve?
Absolutely. If they use a generic K factor, their applied torque will result in wildly inaccurate bolt tension.
The source also highlights that 550 Extreme improves torque repeatability when used with specialized coated bolting assemblies. It specifically names XY-LAN and dock steel.
Yes, those are highly specialized fluoropolymer and alloy coatings.
But those coatings already drastically alter the surface tension of the bolt, right? Why add grease to a coated bolt?
Which is precisely why an intervening compound is necessary. A PTFE coating like XY-LAN behaves very differently under load than bare steel.
Oh, I get it.
Yeah, 550 Extreme acts as a normalizing layer. It provides a consistent, predictable shear plane between the nut and the coated threads. It ensures the engineer's torque calculations remain reliable regardless of the proprietary polymer coating underneath.
That makes a lot of sense. Now that we know the exact math required to safely apply this compound, let's finally look at the specific high-stakes locations around the globe where this math is put into practice.
The real-world battlefield.
Exactly. I'm marveling at the sheer versatility of this compound. It really pushes back on the idea that industrial grease is just, a brute force product for steel gears.
Right, it's way more versatile.
The data sheet lists compatibility with steel, stainless steel, cast iron, titanium, copper, brass, alloys, and plastic. It targets threaded fasteners, valve stems, slides, fittings, guides, and keyways.
If we connect this to the bigger picture, its critical role in petrochemical plant maintenance is a great example. It prevents heat freeze on coker drumheads and heat exchanger breech blocks.
What exactly is a coker drumhead dealing with?
Well, a coker drum is processing heavy residual crude oil. It cycles from ambient temperatures up to 900 degrees Fahrenheit and back down again continuously.
Oh, wow. So expanding and shrinking constantly.
Exactly. That extreme thermal expansion and contraction stretches and warps the base bolting. Without a compound like this maintaining that lamellar slip plane, Dismantling a coker drumhead for routine maintenance would result in thousands of snapped bolts.
It also specifies that when used in tandem with graphite stem packings, 550 Extreme improves conformance to API 622 low E criteria.
Which is huge for environmental standards.
Right. Low E meaning low emissions. So it's actively helping these massive industrial valves maintain a tighter seal against fugitive chemical emissions escaping into the atmosphere.
And we also see its military and aerospace validations, proving its pedigree beyond just the petrochemical sector.
Yeah, the specs note it conforms to military specification MIL PRF 907F and Raytheon specification M8656839 Type 3.
Earning those military and airspace specs really proves the formulation's stability under shock, vibration, and rapid altitude or thermal shifts.
Definitely, but the manufacturer does draw one very specific hard line in the text regarding its use with gases like LPG, liquid petroleum gas.
Yes, this is a crucial distinction.
It states that the product is an effective anti-seize for use with LPG and other gases, but then adds this bold caveat. For sealing applications, use V2.
That caveat highlights the fundamental difference between an anti-seize and a thread sealant. 5 and 50 Extreme prevents metal binding and allows for safe dismantling.
Right.
But a high-pressure gas molecule can still travel up the microscopic helical path of the threads. If the primary mechanical goal is to permanently block that gas path, you need a compound engineered to physically plug those microscopic gaps.
Which is why they direct the user to their V2 sealant instead.
Exactly. Precision engineering requires deploying the exact right mechanism for the required outcome.
Tracing the journey of this single technical data sheet completely changes the perspective on how infrastructure survives.
It really does.
We started with a delicate chemical architecture, right? Calcium sulfonate tadpoles sealing out oxygen, while synthetic graphite and molybdenum disulfide act as microscopic playing cards to manage shear friction.
Then we explored the moly paradox.
Right, discovering how careful formulation prevents catastrophic friction drops during 400-degree hot torquing. We unpacked testing metrics like the 100 load wear index and survival ranges from -265 all the way to 2400 degrees Fahrenheit.
And we saw how the dynamic net factor curve allows engineers to safely tension titanium joints, military hardware, and coker drumheads.
It's just wild.
It reveals that the stability of our most massive structures relies entirely on the invisible mathematics operating in the microscopic layers between the fasteners.
For you listening, the next time you see a refinery glowing on the horizon, or you drive your car over a massive steel suspension bridge, or even just see heavy machinery at a construction site, you aren't just looking at static metal.
Not at all.
You are looking at a silent, high-temperature war being waged by extreme chemical engineering, fighting to keep those colossal forces predictable and under control.
You know, looking at the sheer effort required to engineer this level of predictable friction, it leaves you with a fascinating philosophical takeaway.
What's that?
Well, as industries move aggressively toward 3D-printed, solid-state, unibody construction, essentially eliminating bolts, fasteners, and joints entirely to save weight and increase absolute rigidity, are we engineering ourselves into a corner?
How do you mean?
If this specialized anti-seize compound is precisely engineered not to bind things permanently, but to allow structures under immense heat and pressure to be safely dismantled and repaired, what does that teach us about our own rigid systems?
Oh, wow. That's a profound way to look at it.
Right. Whether it's how we build our organizations, our cities, or even our relationships, perhaps the secret to surviving extreme stress isn't holding on as tightly as possible. Maybe true structural resilience is found in engineering the ability to let go, take things apart, and adapt when it's time.